In this video, I'd like to share a little bit more information about the Fundamental Theorem of Calculus, or FTC for short. Now, the Fundamental Theorem of Calculus generally talks about areas underneath a curve. And before we talk about the FTC specifically, let's just talk about an area function that's developed because of the Fundamental Theorem. If we're going to let f be a function that's continuous, and it's important that it's continuous here in order for this rule to work, for any t value that's greater than a, now notice that a is our lower boundary here and t is the variable of integration, then the area underneath that curve with the left endpoint at a, so starting at a and increasing towards x, is represented by this integral. And what's interesting about this is that the area function is based on the variable x. So as x changes, then the area will change. So we're going to show an animation here in just a second, but if we've got a curve, the boundary on the left is going to be fixed, some arbitrary value a, but as x changes to different positions, then the area underneath the curve is going to change to different values as well. So the area function is dependent upon essentially the right-hand boundary of the function. Now, one way that we can illustrate that is with a diagram like this. The function f of x is 2 times sine x plus 1. That's what created this curve. Now, in the area function, we're going to switch that variable to f of t, because now f of t and a t-axis is what generates the shape. The variable x is now reserved for the variable, the right-hand boundary of our integral, and the area is going to accumulate as we slide our x value further and further to the right. So at point 0, there is no area underneath that curve, right? Because from 0 to 0, there's no width, no area. But as I drag this slider to the right, you can start to see what's happening. This x value indicates a position along the f of t function, so the function result here. But you'll notice what's happening to the area function. The accumulated area continues to increase. So as we slide to the right, the amount of area in this pink section is on the rise, and that's indicated by the graph here in red. Now, you should recall that once we hit this point, something interesting happens. The function value starts to drop, and the area underneath the x-axis is now going to be counted as negative. So the accumulated change is going to drop just a little bit, and it does. And then here again, the function results tend to be positive. The next amount of area calculated is positive, so the area in total begins to increase again. So let's see if I can zoom out here. As I continue along this path, you'll notice that there's always going to be more area above the x-axis than below. So even though we see points or periods of decreasing area, it never turns out to be a negative calculated result. The area always tends to be positive. The accumulated area is always positive, I should say. And so, again, this area function doesn't, I guess it does have some of the similarities, or it's related to the original function itself, but the shape and the behavior of the area function is quite different than the function that was used to create the boundaries for integration. And so, with that in mind, that allows us to talk a little bit more clearly about the FTC. Now, if we continue our discussion on this area function, based on one of the examples from the last video, we're being told now that the area function a of x is dependent upon the behavior of this curve, or linear equation, and the area function is dependent upon x, our right-hand boundary. So we would like to find the function that describes the accumulated change, or the total area underneath this curve, starting at an x value of 2 and increasing to whatever position that x ends up being in. So if x ends up being here, then the area is small. If x ends up being here, off to the right-hand side, then the area becomes quite a bit larger. And so as the variable x changes positions, we would like to have a function a that accounts for that. So part A here. What would the area at an x value of 2 be? Well, this is actually pretty easy. because with an x value of 2, we're saying that our upper boundary is 2. Our function is 2t plus 3 with respect to t. And if we had a region whose boundary on the left was 2 and on the right is 2, well, now we're just talking about the slimmest of lines with no width whatsoever. So the accumulated area between 2 and 2 is going to be 0. The area function evaluated at 5 would be the result of the integral from 2 to 5 of 2t plus 3 with respect to t. And in this case, we're talking about a trapezoid whose height is 3, base 1 is 7, because 2 times 2 plus 3 is 7, and whose base 2 is 13, because this x value is now 5. 2 times 5 plus 3 is 13. And therefore, the area using our trapezoid formula would be 7 plus 13 divided by 2 times 3, which ends up being 10 times 3, or 30 square units. And then part C asks us to find and graph the area function AX, A of x. Well, A of x would be equal to the integral from 2 to x of the function 2t plus 3 with respect to t. But how on earth do we evaluate that? We've not formally seen this process. And well, that's where the fundamental theorem comes into play. Now, the fundamental theorem takes our area function and expands upon it just a little bit, and it states that the derivative of our area function, which would be the derivative of this function here, ends up being this internal function not evaluated at t any longer, but being evaluated at x. So if the derivative of our area function is simply the function of the boundaries evaluated at x, then it stands to reason that our area function a of x is simply the antiderivative of the original function plus c. So, with that known, let's go after our area function above by finding the antiderivative of this particular function. And it sure would be nice if we were able to calculate c as well. So, the antiderivative, let's say f of x is 2x plus 3, because we can now make that switch. We're talking about the antiderivative of the area function. So our antiderivative would have to then be x squared plus 3x plus c, using our antiderivative rules from before. Now, in order to find c, we just need one initial value, and we ended up having two of them in this case. I'm going to use this first one, though. We knew that the area at 2 ended up being 0. So I'm going to say this, that the antiderivative at 2, so that would be 2 squared plus 3 times 2 plus c. Well, this area ended up being 0. So 0 is equal to 4 plus 6 plus c. Therefore, c by itself, after we subtract 4 and 6 from both sides, must be negative 10. So as it turns out, our antiderivative with our initial value, so that we can locate this correctly, is x squared plus 3x minus 10. And this function is indeed our area function as well. Now, in the notes, I did provide a graph of this function over here, and hopefully we can see this result. When x is 2, the area ends up being 0. When x is 3, it's kind of hard to tell, but the area would be the y result on that function. When x is 4 or 5 or so on, we can now calculate the area by simply substituting x into this formula. In part B, we were asked to find the area based on an upper boundary of 5, and we thought that that would be 30. Well, sure enough, if I jump over to 5 on the x-axis right here, and travel upward towards the function result calculated would also be 30. F evaluated at 5 squared plus 3 times 5 minus 10 is 30. 25 plus 15 was 40. 40 minus 10 is 30. So now, and this is a big jump here, but hopefully you can start to make sense of this. Now, when we're talking about the original function, f of x, or f of t, depending on which variable you're considering, when the area needs to be calculated, the area between 2 and 5, well, the area function was based on this lower limit of 2 and the upper boundary of x, in this case being 5. If this lower boundary wasn't 2 after all, but some other value, and this upper boundary ended up being some other value, well, as it turns out, as the positions along this t-axis change, we can simply calculate the total area by evaluating the difference in our area function. So, for example, if I wanted to calculate the area underneath this curve between, say, 3 and 4, well, the area function at 4 and the area function at 3 can be evaluated, and the difference between those two would represent the area in between 3 and 4 in our original function. And let me show you what I mean by that. Okay, we're going to evaluate the area function at 4. I'll erase this for the time being. And so when we evaluate this area function at 4, when we substitute 4 into this function, I end up getting a result of 18. Now 18 would be the area between 2 and 4. Okay, so that's this area. Now, if I have the area evaluated at 3, this calculated result comes out to be 8. And so the area between 2 and 3 ends up being 8. Now, what if I wanted the area here between 3 and 4? Well, it stands to reason I would take the area associated with the right-hand boundary of 4 and subtract the area associated with the right-hand boundary of 3, and that's what's going to leave us with the area here in between. So, instead of finding the area between 2 and 4 and the area between 2 and 3, or I should say, because we can find the area between 2 and 4 and the area between 2 and 3, and subtracting those two, that's essentially going to tell us the difference between these two areas, and the difference between those two is 10 units. And now it's believed that the area beneath this curve between 3 and 4 is 10 square units. And we'll check that with a calculator. So if I take the integral, so calculus integral between 3 and 4 of our function 2t plus 3 with respect to t. Now again, we said the area between 2 and 4 was 18, the area between 2 and 3 was 8, so the leftover area in between 3 and 4 should be 10, and when we press enter here, what do you know? We get a result of 10. That's no coincidence. As it turns out, this is an extension of our fundamental theorem of calculus. Again, we're saying that the derivative of our area function is the antiderivative of the interior function. And when we're computing the area between two boundaries, this part 2, the second part of the fundamental theorem, ends up being much more helpful. In order to evaluate the area between two boundaries, we need to identify the antiderivative and evaluate the antiderivative at our upper boundary and our lower boundary and subtract the areas associated with each. So this part 2 of the FTC is more helpful when we calculate the areas underneath a curve, especially in the event of trying to describe accumulated change. We end up using this technique an awful lot. And because of that, we do end up using a bit of an abbreviated notation here. If, for example, we're being asked to calculate a definite integral between a and b, our boundaries a and b, of a function, we know that we're going to evaluate the antiderivative at b and at a and subtract those two. So a lot of times what we do is we use this shorthand notation here, and we simply indicate the antiderivative f of x with a vertical bar, and we write a and b at the bottom and the top of that bar. This notation implies that we're taking the antiderivative at b and subtracting the antiderivative at a in order to calculate the area in between those two boundaries. So let me show you an example. In order to find the area under this curve between an x value of 0 and an x value of 10, we must first find the antiderivative of this function. Now, the way we found the antiderivative of a power function in the past was to push the coefficient towards the front and increase the power by 1 and then immediately divide by that new power. We can do the same thing for our second term. Now we have x cubed over 3 plus c. And this resulting integral would be this expression evaluated at both 10 and 0 and subtract the difference between. So we can clean this up just a little bit, and we've got 30x squared minus 2x cubed plus c evaluated at 0 and 10, subtracting the results in between. And just to be abundantly clear, I'll show all of my work this time. So this shorthand notation implies that we're taking 30 times 10 squared minus 2 times 10 cubed plus c, and we're subtracting from that 30 times 0 squared minus 2 times 0 cubed plus c. Now, even though c is some arbitrary constant, it is a single value within the problem. So as we perform our subtraction, this c minus this c will cancel. And right now I'm left with 3,000 minus 2,000 minus 0 minus 0. So it sure looks like to me that this area is going to be 1,000 units. And if we were to check with a calculator, it would look something like this. We'll call upon the calculus menu and evaluate an integral. The boundary of integration is 0 to 10. The function was 6dx minus 6x squared with respect to x, and the end result is indeed 1,000. So we can use a calculator if we need to, but if possible, and perhaps you'll be tested on your ability to do so, if possible, we can also do this by hand as well, or if necessary, we can do this by hand. Part B. Well, I'm going to treat this 3 as a coefficient, a multiplier times sine of x. So I know that the antiderivative of 3 times sine of x would be 3 times the antiderivative, or the definite integral in this case, of sine of x dx. And so that would be 3 times. Now, the antiderivative of sine is the opposite of cosine plus c. And we're going to evaluate that at 0 and 2 pi and find the difference between. So as we evaluate this result, we have 3 times. I'm going to put this on the outside of a larger grouping symbol. So we've got negative cosine of 2 pi plus c minus negative cosine of 0 plus c. So that's going to be 3 times, now cosine of 2 pi, I'm thinking about my unit circle here, 2 pi is this position here, so cosine, the x value at that spot is 1. So we have negative 1 plus c minus, now a negative cosine, well that's interesting, we've got negative times cosine at 0, cosine at 0 is also 1, so we've got a negative 1 plus c again. And now we've got an interesting result. This negative 1 minus this negative 1 will cancel. This c minus that c will cancel. And now we're left with 3 times 0, which indeed is 0. So the accumulated area, or the accumulated change on 3 sine of x between 0 and 2 pi is going to be 0. Now in our third example, it might be helpful to consider rewriting this. Now remember, if there's a division of a single denominator, we can essentially create 2 fractions with each fraction composed of the same denominator. So that's what I'm going to do here. We're going to find the integral from 1/16 to 1/4 of radical t over t minus 1 over radical t with respect to t. Now mentally I'm going to think of this square root as a 1/2 power. And now if I have 1/2 power over a power of 1, I'm going to treat that as t to the negative 1/2 power. So there's a little bit of mental math that's going on here. 1/16, 1/4, t to the negative 1/2 power minus 1 over t with respect to t. Now I'm not going to make that change. I'm not going to use the same trick here, because when we think about our antiderivative rules for powers, they don't work when the exponent is negative 1. In fact, our power rule explicitly stated that we can't use the power rule when our exponent is negative 1. And the reason for that is because there's a whole nother function whose derivative is equal to 1 over t. Remember, the derivative with respect to x of natural log of x would be equal to 1 over x. So the antiderivative of 1 over t is going to have to be the natural log of t. So as far as our antiderivatives go, we can use the power rule on this term. So that's adding 1, that becomes t to the 1/2 power divided by 1/2. So t to the 1/2 power divided by 1/2, that takes care of this term. Minus, now the antiderivative of 1 over t ends up being the natural log of t. And of course plus c for our unknown constant. If we are to evaluate this function at 1/4 and 1/16, then the difference between those two results will indicate our area underneath the curve. Well, these boundaries of integration ended up being pretty nice for us, because I'm going to do this. When we divide by 1/2, that's the same as multiplying by 2. And again, t to the 1/2 power is a square root. So I want the square root of a fourth, square root of 1/4 times 2 minus the natural log of, I keep screwing that up, natural log of 1/4 plus c. So that's our first expression. From that we'll subtract the 2 times the square root of a 16th minus the natural log of a 16th plus c. Again, in the process of subtraction, the c values will cancel. The square root of a fourth, what value multiplies by itself to equal a fourth? Well, that's 1/2. So we now have 2 times 1/2 minus the natural log of 1/4 minus 2 times 1/4, the square root of a 16th is a fourth, minus the natural log of a 16th. And if we distribute and combine like terms and drop all parentheses, we're now looking at 2 times 1/2, which is 1, minus the natural log of a fourth, minus 2 times a fourth. Well, 1/4 of 2 is 1/2. minus a negative natural log of 16, so we'll say plus the natural log of 1/16. And so we have 1 minus a half, which is 1/2 minus the natural log of a fourth plus a natural log of 1/16. And we've got a precise answer for the area underneath this curve. Now, if you're looking at your notes below, you can see a sketch of these equations. And so in example A, we said the area underneath the curve between 0 and 10 should be 1,000. Well, here's that shape, and if the graph reaches 150, has a width of 10, but it's a curve along the way, I think it seems reasonable that the area could be 1,000. In part B, we said that the area ends up being 0. Well, here's a graph of that sine wave between 0 and 2 pi, and sure enough, we've got a positive and a negative component. Those two are equivalent in size, so the net area is 0. And then lastly down here, now this is one we didn't finish computing, but the exact result I predict is this value, and it kind of looks like that this result should be a negative number. And I'm guessing that it's negative because according to this graph, the entire area is below the curve. So let's see. We'll use the calculator to evaluate this integral first, and we'll see if that's a negative number. So on the calculator, we'll pull up our calculus menu and evaluate the integral from 1/16 to 1/4. And we're evaluating the function, which is a fraction in and of itself. And in the numerator, we have the square root of t minus 1 over the denominator of just the variable t, and we're integrating this with respect to t. And there's a precise result, and there's our calculated result. So negative 0.8863. So the area definitely is negative. The area is equal to negative 0.8863. So now's the real test. Does this calculated result give us the same number? And so here we have that expression, 1/2 minus the natural log of a fourth plus the natural log of a 16th. 1/2 minus natural log of a fourth plus natural log of 16th. A little bit nervous here. Let's see what we get. Negative 0.88629. The two results appear to be the same. Now, I was a bit nervous because you'll notice that the calculator computed a precise result of 1/2 minus 2 times natural log of 2. But our expression down here did not contain 2 times natural log of 2. So I'm sure it used some logarithm rules in order to simplify this. In fact, if I copy this and allow it to produce the exact result, I do get the same answer. But that's not overly critical for this. I think this expression would be good as an answer. And if I did ask for the decimal equivalent, calling it negative 0.8863 would be just fine. So again, I hope that this video was helpful to you. I understand that there's a fair amount of theoretical discussion, especially with the definitions of the area function as well as our fundamental theorem of calculus. But the more we talk about it, the more you're exposed to it, I think the more it'll start to sink in and make more sense. If you have further questions, please do let me know. Otherwise, thanks for watching.